So we ended our previous lecture doing a clicker problem where we were calculating heat using our Q equals Cm delta T equation. Now I want to do another quick practice problem with that equation just to wrap up our lesson on calculating heat, where instead of calculating the heat, we actually want to use this equation to find the mass. So the question asks us, a piece of copper was heated and it required 8,460 joules of heat to raise the temperature from 19.3 degrees Celsius to 68.9 degrees Celsius. If the specific heat of copper is 0.385 joules per gram degree Celsius, what is the mass of the copper sample being heated? Now you can do one of two things. You can either take this equation, rearrange it, and solve for mass before you enter in the numbers, or you can enter in the numbers and then solve for m as if it was the variable x. You can do it either way, whichever way you are most comfortable solving mathematical equations and rearranging them to solve for the unknown variable. Let's see. So all of our numbers that we have are in the correct units that we need them to. The only thing we have to do is calculate our delta T. So we know our Q is 8,460 joules, and that is going to equal our specific heat of copper, which is 0.385 joules per gram degree Celsius, multiplied by the mass, which is what we're looking for, and then multiplied by the difference in the temperature, so 68.9 degrees Celsius minus 19.3 degrees Celsius. And that gives us a difference of 49.6 degrees Celsius. So to solve for m, we just divide both sides. So our equation can be arranged to be m is equal to Q divided by C delta T. So I have all those values in here. So I get that our mass is going to be equal to 443.0247 grams. So I just took that 8,460, divided it by 0.385, and which was multiplied by 49.6. So I take my specific heat, multiply by my temperature, whatever value I get from there, I then use it to divide with the 8,460. So we're not done yet. We have to look at our sig figs. So I'm just going to highlight our sig figs in red here. So let's see, we have 4 sig figs from that 8,460. Since this is a constant, it is for that specific element, it does not contribute to sig figs, so we don't use that for sig figs. And then we have 3 sig figs from our 19.3 and our 68.9. However, since we're using it in addition subtraction, we have to use our addition subtraction rules. They both have 1 decimal place here at the end. So our final answer for degrees Celsius is going to be to our last decimal place, which means 49.6 has 3 sig figs. So our final answer for mass should have 3 sig figs, because our only options are the 4 and the 3. So this would be 443 grams of copper. Now what you're going to do after you finish watching this lecture, we're going to move on to calorimetry, but there's a worksheet that you are going to do. And that is going to be due on Wednesday. And that worksheet, the first part of that worksheet is going through similar problems such as this, where you're using the heat equation to calculate something, whether that's heat, specific heat, delta T, whatever it may be. What I want you to do is to start using this Q equation. I want you to start solving it for all the different variables, getting used to rearranging it in the way that you need it to solve for whatever variable the question is asking for. Do any conversions that you may need to do, whether that's kilojoules, milligrams, whatever it is. get comfortable using this equation, and that's what those 3 problems are going to have you do in the worksheet. The second half of that worksheet is then going to have problems about our next topic, which is calorimetry. So calorimetry is an experimental technique. So as I was saying in our previous lecture, there's no way to directly measure heat or that value of Q. We can measure mass, we can measure temperature, so we can use a balance to measure mass, we can use a thermometer to measure temperature, but we don't have a specific instrument like a balance or a thermometer to measure the heat. But what we can do is we can use values to derive the heat, and the experimental technique to do that is called calorimetry. So calorimetry provides us with an experimental technique to measure heat changes using a thermometer, knowing mass, things like that, so that we can utilize that Q equals cm delta T equation. The calorimeter is the actual device used to measure those heat changes. And a calorimeter can come in many different forms. So here we have a coffee cup calorimeter. So this is a coffee cup calorimeter. It's literally made out of styrofoam cups. So you put 2 styrofoam cups together. One of those styrofoam cups has water in it. If you know the mass of the water and the mass of whatever sample you're putting in there or reacting in there, you throw a thermometer in there. You're measuring the heat difference in the water. So the water is going to start to heat up. It'll start to get hot. And that thermometer temp is going to get higher. You measure that difference in the temperature. That's your delta T. If you know the water, you know its mass, meaning you can solve for Q because we know the specific heat of water. So it doesn't take much to find that Q. So here we're using styrofoam cups. If you're in the lab course, you'll use a styrofoam cup, coffee cup calorimeter. You'll also use a soda can calorimeter, which is similar. It's using an aluminum can. You're burning a piece of food under that can and trapping the heat in the water that's in the can, and then measuring that temperature difference. Okay, so a calorimeter doesn't have to be a fancy device. Are there fancy calorimeters? Yes, those are what we use to measure calories in our food. So the labels on our food are going to tell us the calories, the amount of energy units that we can get out from that food. And in order to measure that, they have to use something a little bit more sophisticated than a coffee cup calorimeter, and that's called a bomb calorimeter. It's literally where they do a small scale explosion in a calorimeter where the surroundings are really just the water that's inside, the system is the reaction, the explosion of whatever's going on. So there's many different types of calorimeters. So in calorimetry, a substance is placed into a solution and then the heat is transferred. So here we have the system. So here's our system here. This can be metal. This can be a metal where we're looking for this, if we know the specific heat or we're looking for the specific heat, or it could be some sort of reaction. There could be a reaction going on within that calorimeter. But somehow heat is transferred, whether that's from the system to the surroundings or from, let's go change the color for that, from the surroundings to the system. So somehow that heat is transferred. The temperature change of that solution is recorded, like we were talking about on the previous slide. That temperature change is recorded in the calorimeter, and that temperature change and the mass can be used to derive the amount of heat transferred in that process. So here's where we can use those values. If the change in temperature is known, and the mass and the specific heat of the solution in the calorimeter is known, then the heat involved can be determined. And that's just using Q equals Cm delta T. Now we're going to use it in a slightly different way, which we'll talk about here in a second. But what I want to talk about first is the difference between our system and our surroundings, as well as how that relates to what we were talking about in our previous lecture on exothermic and endothermic reactions. So calorimeters are well insulated. meaning that whatever is inside is going to be your system and your surroundings, and that's it. Whatever's on the outside of that calorimeter is not going to have any effect on the reaction or the transfer of heat inside of that calorimeter. So this right here, the calorimeter itself, this is our universe. That's our miniature universe. Because what's on the outside here, what's out here doesn't matter. It's irrelevant. So in this case, our system is whatever substance is either being placed into solution, so that whatever that metal or compound is, or whatever is being reacted in the solution. The surroundings is then the solution itself. And that whole calorimeter makes up the universe total. So because we are looking at system and surroundings, we have to remember that the law of conservation of energy tells us that energy cannot be created or destroyed. So in our small calorimeter universe here, the heat of the system plus the heat of the surroundings has to equal 0 because the heat is being transferred from one to the other. Okay, so they have to equal 0. There cannot be any difference in the heat besides what is already there because it has to be fully transferred. So we can make a relationship between those, and that can tell us the difference between our exothermic and endothermic reactions. So if it's an exothermic reaction, then heat is going to be lost by the system. Okay, so whatever is, say, our block of metal, okay, whatever that is, the heat is being lost and then is being fully gained by the surroundings. So heat is going out. It's going out into surroundings, out into the solution, meaning that the heat of the surroundings is decreasing or going negative, or sorry, is changing. It's going to be completely opposite of the heat of the system itself. If it's an endothermic reaction, it is now the opposite. Let me erase this so we can show it the other way, and I'll go blue. So we have our system, and the heat is being transferred from the surroundings into the system itself. So that means that our system is going to be taking on the heat, and our surroundings are going to be providing it. Now, I understand that the negatives can kind of not make sense here, so I did want to make a quick note about that. The negative signs here are confusing. I believe that in a lot of this thermodynamics and thermochemistry stuff, the signs are probably the most confusing point about what we're looking at. So the negative sign here just shows where the heat is being transferred to. So in this example, the surroundings, the Q surroundings has the negative value, meaning it's exothermic. The heat is being transferred to the surroundings, therefore our negative sign is going to the surroundings. Okay, for an endothermic reaction, since this is where our negative is, the system is what's gaining the heat. The heat is being transferred to the system, so that Q has the negative. Mathematically, the signs will end up working out because really all it's saying is that the heat is opposite of what it was. So the heat of the surroundings is opposite of the heat of the system. And the delta T's, since we're using final minus initial, end up working out to show us the negatives on whichever side they're necessarily needed on. So as long as you're keeping your delta T's, your finals, and your initials correct, and remembering that the negative just means that the heat is being transferred, and it just means that the heat is opposite of the other, then you are good to go. So I have a quick practice here that's going to show us how we're going to use our Q is equal to Cm delta T equation for a calorimetry problem. Now, what we were looking at before was we just had a pan. Here's my pan. Excuse me, I'm not an artist. There's a pan, and I heated it up, and I only worried about what was changing about the pan itself. I didn't have to worry about anything else but just the compound of the pan or whatever object I was looking at. But with a calorimeter, we have to look at both the water and the metal or the reaction that's going on, inside of our reaction vessel, inside of our calorimeter. Okay, so we actually have two things that we have to worry about. We have the heat of the metal and the heat of the water. And we know that they're going to be opposite values of each other because the heat, we are assuming, is being fully transferred from one to the other. So in our example here, a 92.9 gram piece of metal is heated to 178 degrees Celsius, and then it's quickly transferred to 75 milliliters of water with an initial temperature of 24 degrees Celsius. So the water has an initial temperature of 24 degrees C, and the metal has an initial temperature of 178 degrees C. After 5 minutes, the metal and the water are going to reach the same temperature. They're going to come to an equilibrium, and that temperature is 29.7 degrees C. What we want to do is determine the specific heat of the metal. Okay, so we know the specific heat of water. Our density of water is going to come into play here because our density has units of grams per milliliter, and my value for water is in milliliters, but I do somehow need a mass, so we'll use that to convert. But what we're going to have to do is use this equation here. I'm going to erase these. We're going to use this Q of the metal is equal to the negative Q of the water and our Q equations themselves in order to solve for the C of the metal. So if we really think about this, Q of the metal is C metal times the mass of the metal times the change in the temperature of the metal. Okay, because Q is equal to Cm delta T. So I have Cm delta T, that's Q of the metal. So that's the same thing that I wrote here. Then for Q of the water, I just need to make sure I add my negative there. Okay, the delta T's are going to end up having our negatives work out, so you just have to make sure you include this negative here. Okay, and now it's just the C of the water, the specific heat of the water, multiplied by the mass of the water times the change in the temperature of the water. So we're not just using our heat equation for just those three variables. Instead, we're taking those three variables and setting them equal to each other because of the law of conservation of energy, where we're saying, well, all of the energy has to be exchanged from one portion to the other, from our system to our surroundings. Okay, so now it just becomes a 6-variable problem where we know all 5 variables and we're solving for the 6th. So we're solving for the specific heat of the metal because we know the mass of the metal, we know the temperature change of the metal, we know the specific heat of the water, we know the mass of the water, and we know the change in the temperature of the water. My note here that I have for you all is that the final temperatures for both the metal and the water are the same. They came to the same temperature. Okay, that's that, what was it, 29.7? But our initial temperatures are going to be different, meaning that the delta T of the metal and the delta T of the water are not the same. So it's not like they cancel each other out. So you have to keep that in mind. So let's work through this problem. So we have Cn, Mn, delta T of the metal. Cn is what we're looking for. The mass of the metal was 92.9 grams. The delta T of the metal was 29.7 degrees C minus 178.0 degrees C. So that's our final minus initial. And this gives us a delta T of negative 148.3. You gotta keep that negative there. We could do the same thing for C of water, M of water, delta T of the water. The C of water is that 4.184 joules per gram degree Celsius. The mass of the water, as we were saying before, we have to use our density of water and our volume of water. So we know that we have 75 milliliters, and in the density of water is 1.00 grams per 1 milliliter. So this equals 75.0 grams for our mass of water. And then our delta T of the water is our final, that 29.7. That's the same as our metal, but our initial temperature is 24.0 degrees Celsius. And this gives us a delta T of 5.7 degrees C. Okay, so let's solve this. So we know 5 of our variables. We're just solving for our 6th. So it really is Cm times 92.9 grams times that negative 148.3 degrees C. That's going to be equal to negative, we got to have that negative because remember we have this negative here. Got to bring that negative down. At 4.184 joules per gram degrees Celsius times the mass of water, which was 75.0 grams, times the change in temperature, 5.7 degrees C. Okay, so we have degrees C that are going to cancel out and grams that are going to cancel out. So we can simplify before we solve. So we get, let's see, on this side of our equation, we get negative 1788.66 joules. So I'm left with joules there. And then I get Cm times negative 13777.07 grams degrees Celsius. Sorry, I ran out of room there. Okay. So we got to make sure we're keeping our negative signs. This is a negative, this is a negative. So we're going to see that those negatives are going to end up canceling. So we're going to be left with a positive, which is what we want for a specific heat. So we have Cm is going to be equal to negative 1788.66 joules divided by negative 1377.07 grams degrees Celsius. If we look at our units, joules per gram degree Celsius is the unit we want for a specific heat, so that's great. We get a value after doing that ratio of 0.1298287 joules per gram degree Celsius. But we're not done yet. We need to look at sig figs really quick. So if you look at the numbers that are given to us, I have 3 sig figs here. When I do my subtraction in my delta T, I have to keep my 1 decimal place, so that gives me 4 sig figs there. Let's see, this doesn't count towards sig figs. The CW, the specific heat of water, doesn't count towards sig figs. The 75 milliliters, 75.0 milliliters, and the 75.0 grams have 3 significant figures. And then when I do my delta T of water, since we're doing addition subtraction, we have to keep our tenths place. So that would be here, meaning that 5.7 has 2 significant figures. So our final answer needs to have 2 significant figures. So this would be 0.13 joules per gram degrees Celsius. And that is our final answer for that problem. Now, you will have practice problems on this in your worksheet. Again, you should have everything in the appropriate number of sig figs. So make sure when you're doing your delta T, this is where your sig figs are always going to get messed up. I promise you will always get messed up with the delta T sig figs. I see it all the time. So just make sure you're keeping an eye on your delta T when it comes to sig figs, because you are doing mixed operations sig figs. So if you need a review on mixed operations sig figs, you can go to Appendix B in your textbook for mixed operations sig figs to review that. Okay, but you will have a couple problems similar to this in your practice worksheet that is available on e-learning. So Just to move forward a little bit, when we're talking about calorimetry, so what we were talking about previously was calorimetry when I put a metal into the water. That was our previous example. But now I want to talk about chemical reactions. This is the chemistry class. We care about the reactions that are happening. So when we're doing calorimetry to determine the heat that's involved in a chemical reaction, everything we've been discussing previously with the system and the surroundings and Q is equal to Q and all that, it's the same. It's the same principles. You just may have to think about it a little bit differently. So because of the conservation, law of conservation of energy, when we're doing a chemical reaction, the heat that is produced by the reaction or the system has to be equal but opposite to the heat that is lost by the solution or gained by the solution. So they have to be equal but opposite to each other. So I have a little kind of better picture of what I'm saying here, where the Q of the reaction, get a good color, let's do red. So in the same way that we had Q of system and surroundings in our previous slides, we have Q reaction plus Q solution has to equal 0 because of the law of conservation of energy. So whatever heat is produced has to be equal to 0. So we can say that the Q of the reaction is equal to the negative Q of the solution in the same way that we said the Q of the system is equal to the negative Q of the surroundings. Okay, and again, this is just the concept that's at the heart of calorimetry problems, is this equal but opposite value of heat, because we're making the large assumption that all of the heat is transferred from the system and only to the surroundings, and that the outside of that calorimeter does not matter. When you're in the lab, if you're taking the lab course, you're going to find that that assumption is not always a great one. Sometimes we're losing heat, especially if we're burning food, so you're going to explore that more in the lab. I think the best way to kind of think about these reactions and relating them to calorimetry is to just do an example. So this is worked example 9.5 from your textbook, from your OpenStax textbook. So if you get a little lost or have a little bit of confusion, please go there and we can follow along with the worked example in your textbook. So the question or the problem says that we have 50 milliliters of a 1 molar HCl and 50 milliliters of a 1 molar NaOH solution. Both are at 22 degrees C. Sorry, that is missing their temperature. And they are added to a coffee cup calorimeter, and the reaction proceeds and reaches a maximum temperature of 28.9 degrees C. We want to know what the approximate amount of heat produced is by that reaction. So if we were to touch the reaction vessel, it'll get a little bit warm, and we want to know how much heat is actually being produced. Now I have our reaction here. We know our HCl and our NaOH are aqueous solutions. Okay, so they're already in solution. We have their volumes, and we know that we're going to create salt water and water itself. Okay, aqueous, NaCl, and water. So our reaction is balanced. Always double check that you're balancing your reactions. So I want to just highlight what we know from this problem. So we know that Q of the reaction is going to be equal to the negative Q of the solution. We know our Q equations. What we want to know is what is the reaction and what is the solution? Okay, what are we thinking about for a reaction and solution? So what I want you to do is pause the video and think about what is the reaction and what is the solution. If you were to kind of draw that, where would the heat be going from where to where? If I were to draw this out on an atom to atom level, what is the reaction and what is the solution? So pause the video and think about that. So as we come back, our reaction is simply the atoms or the ions of NaCl and NaOH reacting with each other. So if I were to look at a reaction vessel, I'd have a lot of H2Os around. Okay, and these are not the H2Os from here. It's not that. It's the H2Os from the aqueous solution. So in my aqueous solution, I have a bunch of H2O, but I also have H's, Cl minuses, Na pluses, and OH minuses. So I have those ions floating around in solution. So here my reaction, I'm going to try to highlight this, my reaction is simply the Na plus, the OH minus, the H plus, and the Cl minus. It's those ions reacting with each other, and they are transferring energy out into the waters. So our solution is the water from those aqueous solutions. Okay, so because the chemicals are both aqueous, they contain water that is not the water in the product. So the water that they are initially dissolved in prior to the reaction, that water is not participating in this reaction. So whatever is not participating in that reaction is going to be what the solution is. Okay, and the fact that it's water makes this problem significantly easier, because what we don't know, as you may find if you're trying to solve this problem, is I don't know what the specific heat of HCl is to find C to put that in. I don't know the specific heat of NaOH or how they mesh together when they make NaCl. How do I quantify that? Well, if we know the Q of the solution, we can then say, if we know Q of the solution, we know that it is the negative of the Q of the reaction. And since our solution is water, we know C of water, that's going to be that 4.184 joules per gram degree Celsius. We can find the mass, and we can find its delta T. These can all be found. We can find those values from the problem. Okay, so we can find those values. So if we can find the Q of the solution, we don't even need to worry about doing any sort of calculation with C or M or T of the reaction. We could just use that equation there. And so what I want you to do is now solve this problem. Okay, think about what we were just talking about with Q of the reaction and Q of the solution. We want to find this value. This is what the question is asking for. So what is the approximate amount of heat produced by this reaction? What we want to do is say, well, if we know Q of solution, aka water, we want to know C of the water, M of the water, delta T of the water. I'm going to remind us that I forgot my temperature notation there for 22 and that 28.9. Okay, we may have to use our density of water again, because that 50 milliliter solutions that are mixed together, we now have a total volume of 100 milliliters of water. Okay, we're going to assume that that water is in excess. So pause the video, try to solve for that Q of the solution, and find the value of Q reaction using what's in this problem. Okay, so let's solve that. I'm going to get my calculator out here just so I have it on hand. Okay, so we said that the Q of the reaction is equal to the negative Q of the solution. So we want to just find Q of the solution, which is going to be equal to the C of our water, the mass of our water, and our delta T of water. So let's see, we know our C of water, that is going to be that 4.184 joules per gram degree Celsius. If we know that we have 100 milliliters of water, or of solution overall, We know that 1.00 grams is in 1 milliliter for water, so this is 100.0 grams of water. So our mass is 100.0 grams. And then our delta T, let me find a place to write delta T. Let's do delta T right here. That's going to be our 28.9 degrees C minus 22.0 degrees C, which is going to be equal to 28.9 minus 22.0, 6.9 degrees C. And I'm going to highlight this because that's going to be our 2 sig figs for our final answer because of that delta T subtraction. Okay, so this is going to be 6.9 degrees Celsius there. And all we have to do is just then multiply. So 4.184 times 100.0 times 6.9. And we get that the Q of solution is 2886.96 joules. So that's our Q of solution, meaning that our Q of reaction is equal to negative 2886.96 joules. But we have sig figs that we have to worry about, so this would be negative 2900.00 joules. And if we want to put it into 2 sig figs, that would be negative 2.9 times 10 to the 3 joules. Yeah, we didn't ask for kilojoules. So this would be our Q of reaction there. Okay, so my next question for you is a clicker type question. Fortunately, we will not be doing a clicker, but you can think critically about this. So the question is asking, based on your answer here, is the reaction endothermic or exothermic? Is it endothermic or exothermic? Just pause the video, take a second, think about what your answer would be, and then come back. If you said exothermic, you would be right. Okay, your value would be correct. It is an exothermic reaction because our heat is being transferred from our reaction to our solution. So from our system to our surroundings. So I know endothermic and exothermic can be a little difficult to think about with Qs, whether it's an object or a reaction or whatever. So I just have a little bit of a kind of put it into words here. So if heat is transferred from the system to the surroundings, Q is negative and is indicative of an exothermic reaction. If the heat is transferred from the surroundings to the system, Q is positive and is indicative of an endothermic reaction. We can take this one step further and put it into terms of the reaction. So if heat is transferred from the reaction to the solution, that Q is negative and the reaction is exothermic. And then the opposite is if heat is transferred from the solution to the reaction, Q of the reaction is positive and the reaction is endothermic. So our problem dealt with this one right here. The heat is transferred from the reaction to the solution. We have a Q of the reaction that is negative, therefore the reaction is exothermic. It's giving off heat. The heat is going from the reaction to the solution, meaning the solution we feel with our hands, if we were to hold it, is warm. For the other one, for the second example here, this is going to be our ice pack example. So heat is being transferred from the solution to the reaction. So after we crack our ice pack, a reaction is happening, but heat has to be transferred from the solution or from the surroundings into that reaction in order for it to go forward. So the reaction Q value is actually positive, and the reaction is endothermic, and it becomes cold to the touch. Okay? So that is it for our first part of our Chapter 9 discussion. Our next part will be on sections 9.3 and 9.4, which we will get to in class next week. Okay, so that's going to be next week. In the meantime, you have a few things that you need to do. You first need to register your iClicker. You then need to register for Alex. You then need to complete the Gen Chem 1 review. Review homework, and that is for Tuesday, 1/16 at 11:59 p.m. Okay, that's due on Tuesday night. And then you have to complete the calorimetry worksheet that goes along with this lecture to make up for our missed class and submit it to the Dropbox. And I have that Dropbox to be Wednesday, the 17th at 11:59 p.m. So it'll be due after class, just so we can touch base in class if you need it. Okay, so these are the 4 things that you need to get done by class next week.